Welcome viewers. In this video we are going to continue our design of substation equipment foundation in Eurocode. This is stage 6 out of 7. In this we are going to do punching and one-way shear check for the bottom slab. So in the left hand side top you can see a picture which is marked D from the edge of the base slab in plan. So this is a one-way shear. So you can see in the section which is showing a crack line. This is a one-way shear occurred from the face of the column to the base slab at a distance of effective thickness D, and followed by that the next picture is a two-way or punching shear. So here that distance D by 2, this punching shear will occur at a distance of D by 2 around the peripheral to the column. So you can see in the sections where this portion around the column peripheral is used to act as a punching shear to the base slab. So both the shear will occur due to the upward pressure and resisting shear from the column. So these are the various design stages we have seen already. Number 1, in the first stage we have checked that overview of calculation. Second is a foundation and soil parameter loads and load combinations. Followed by that stability check, foundation board design of bottom slab, and now we are in punching and one-way shear. After this we are going to close this series with design of pedestal in upcoming videos. Let me look into that Excel calculation. So in the screen you can see that to check for punching shear on bottom pad. First of all we need to calculate the effective width in X and Y directions, that is B plus T effective and L plus T effective respectively. For B plus T effective we already know that B is a 700 mm or 0.7 meter and T effective is 250 mm or 0.25 meter. So you can see that both small L and small b are 0.7 meter, and T effective which we have calculated in the design of bottom slab is 0.25 meter. So adding these two, 0.95 meter will come. So this is a value for B plus T effective and L plus T effective. And next we need to calculate these table values. So first we will take this case number 21. So V set we already calculated in our previous stability check. So 14.18 kilonewton is our V set. So next value in this column in the table is Q. We need to find out Q is a maximum compression force pedestal. So for per pedestal means as we are having these isolated foundations, the N value will be 1, and V set we already calculated, it is 14.18, and small b and L is a 0.7 meter which we have defined in parameter. The capital D is a foundation depth from the ground level. The T is a small t is thickness of bottom slab. D is a pedestal height above ground. So the GC is a concrete weight density. So we have defined already the capital D is 1.5 meter and small t is 0.3 meter, and small d, that is plinth level, the pedestal above ground level, is 0.3, and GC, that is concrete density, we have considered as 25 kilonewton per meter cube. So applying all this we can able to find out the Q value, which is 32.56. Next column is QS. The QS is a soil resistant. So Q into N, that is number of pedestal, is 1, and P effective. So this value we need to multiply this 0.95 is B effective and L effective respectively, divided by the capital B and L, so which is a bottom pad slab size, which we have assumed as 1.6 by 1.6 meter. By this way we can able to find out the QS value, that is maximum soil resistant, so that is also in kilonewton. Q net is a factor we need to find out, so the QU net is a net factor punching shear, so that is means we need to subtract this QS from Q and multiplying with the factor of safety. So factor of safety we already consider this as per table 2.1 N EN 1992 1 part 1 section 1. So this is a 1.5. So this 1.5 for concrete we have considered. So that is a factor of safety here for punching shear consideration. And so far we have calculated, we have find that V is at QS and QU unit. Then we need to find out the VED. VED is nothing but it is a net factor punching shear stress at foundation pad. So this is the equation to find out that QU net divided by 2 into B effective and L effective into T effective. So all the effective length, width and depth to be multiplied into 2 times, as it is a punching shear, there is a circumferential stress will be applied. So this QU net divided by this we need to apply. So we note that BEF is 0.95 and LEF also 0.95 and TEF is 0.25 meter, and QU net we already calculated this as a 31.62. So applying that we are getting 0.04 as VED, that is net factored punching shear stress at the foundation pad. The value is in megapascal, that is Newton per millimeter square. Similarly, like we need to find out the punching shear carrying capacity of concrete without reinforcement. This is as per class 6.4 of EN 1992. Then we need to find out the punching shear capacity of a concrete without reinforcement, that is without shear reinforcement. So for this is the equations we need to refer: 0.18 divided by gamma C into K into 100 rho I, which is a percentage of steel reinforcement, FCK into 1 divided by power 1 by 3 plus 0.15 sigma Cp greater than, it should be greater than the 0.035 K power 3 by 2 FCK power 1 by 2 plus 0.15 sigma Cp. So these equations we can find out from class 6.2.2 on EN 1992. You can see on the screen, this is the equations which we have followed here. That is here DC value is directly given as 0.18 sigma C. So that's what we have considered here, C or DC as 0.18 divided by gamma C. So gamma C we already know that it is 1.5. We assumed in our load cases. In the introduction part itself we have assumed it is 1.5 as per table 2.9 N. So this rho I we need to calculate, that is area of steel reinforcement, which is to be calculated as reinforcement divided by the area required. So there is a special formula which we need to record, like ASL is a steel reinforcement area divided by width and depth of the pedestal, so that we will be getting that. So however it should be less than 0.02, but in our case it will be more than that, so we can have it 0.02 as rho L, and FCK is a 25 megapascal. So this power 1 by 3, and here 0.15, here K1 it is mentioned here as K1 sigma Cp. So this K1 value is also given here as a 0.15. So that is what we have considered 0.15. So this sigma CP is not applicable for normal method of concreting for our equipment foundations. So generally that will be cast at site or precast. So this pre-stressing is not applicable for this case. So for totally this sigma CP into K1 will be 0. So this we can ignore, and similar like for this minimum value also we can ignore. Only that V minimum we need to consider, and here this CRDC K 100 rho L and FCK power 1/3 to be considered. Also we are going to find out only the stress value in our calculations. So this BW in D also we can ignore. So our unit will be in megapascal, this punching shear carrying capacity. So that is a way we need to calculate this all value. So we already having all the values here. So this K also defined here as 1 plus square root of 200 divided by T, which should be less than or equal to 2. So the D is a dimensions or size of the pedestal. Sorry, it is a thickness of the raft, 250. So applying all this, we are getting 1.85, which is less than 2. So we are considering this 1.895 as K. So here that equation is like this. So for all the cases, this value remains same, 0.45. So as a result of this, we can able to identify that VRDC, that is punching shear carrying capacity of concrete without reinforcement, is having more stress bearing, shear stress bearing compared to the actual, that is net factored punching shear stress at foundation pad. So hence not required, the shear reinforcement is not required in this case, or else we need to design the shear reinforcement accordingly if the VED is exceeding the VRDC. Now coming to the VRDC maximum, that is in no case the VED should not exceed VRD max. So this VRD is a maximum shear carrying capacity of the concrete. So how this can be calculated is, there is a equation which are mentioned in EN 1991. So for that we need to go page 108. So you can see here that value of VRD max, anyway that national annexure to be referred for country code requirement. The recommended value is 0.4 into VFCD, where V is given in expression 6.6 n. So here the 0.4 VFCD we are considered here. So then for V value we need to refer 6.6 n. So for that page number 89 to be referred. So here you can see that V equal to 0.6 into 1 minus FCK divided by 250. So that is what applied here, which is 0.54, and we got this V, and FCT we already calculated from our previous equation. So FCT is nothing but it is a 0.85 into FCK divided by gamma C. So that what we have seen already in our introduction part. So this one, alpha CC into FCK gamma C, and alpha CC is 0.85, whereas gamma C is 1.5, which we already know, and FCK is 25. So applying this, we are getting that VRD max as 3.06. So this actual shear capacity VED, which is already less than this VRD max, then this is safe in punching shear. So next we need to do check for one-way shear on bottom pad. So for that we need to do for both directions along x and y. So we know that partial factors for material for ultimate limit state is 1.5, which we have taken from table 2.1 NEN 1992 part 1 section 1. So net upward pressure of design we have considered based upon the design of bottom pad calculations, which we have already done in our previous part. Distance of face of pedestal from the edge of the pad we need to find out, that is the distance from, so this distance we need to find out. So for that we need to apply this b, capital B minus a small b divided by 2. Similar like for other direction, capital L minus a small l divided by 2. So by applying this, as it is a square footing and a square pedestals, both the directions we are getting 0.45 meter, and critical section for shear from the face of the pedestal is, so this value is dx and dy respectively to the direction of x and y. So in that we need to detect that T effective, that means this distance equal to T effective. So this distance we need to deduct so that we will get this distance. So this is a effective shear distance d1x. So we know that T effective is 0.25 meter. So deducting from 0.45 meter we will get 0.2 meter. So this is for the same value for y direction also. So next one is we need to find out the maximum factored shear forces, so which is equal to delta nu, which is 53.93 kilonewton per meter square multiplied with d1x is a critical section for shear from the face of the pedestal, which is 0.2 meter for both the directions, and 1 is a 1 meter we are considering along the other direction strip, and fs is the partial safety factor 1.5. So applying all these values in this equation, we are getting 16.18 kilonewton, and maximum factored shear strength per meter equal to SVX into 1 meter width we are multiplying as 1000, and T effective, so which should be divided by T effective. So here this multiplication of 1000 means we are converting kilonewton into newton, and T effective we already consider as 0.25 meter, multiplying with 1000 that will come to 250 mm, and again this is breadth in 1 meter strip we are going to consider this factored shear strength. So applying these values, SVX is 16.18 multiplied by 1000 for newton, and T effective is 0.25 multiplied by 1000 will have 250 mm. Applying all this value, we are getting 0.07 megapascal, which is which is less than the calculated shear reinforcement here in punching shear equation. So this 0.45. So hence this one-way shear, this base slab is safe in one-way shear. Similar like for other case also, the value will be remain same because both directions we are having a equal size of the pedestal and size of the base slab. So this is also 0.7 megapascal, which is less than 0.45. Hence no shear reinforcement is required. So with this, one way and punching shear get completed. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.